Hello, everyone.
Hello, everyone.
Okay, so we are live, Olivier. First of all, welcome to our webinar. I think it's several months we have not done one together.
Yeah, it's my first webinar, I believe, on the channel.
On that new channel is the first
Yeah.
one? Oh, because we did a few video recording. That's right.
Yes.
We did, yeah, that's right.
But live webinars is the first time for me.
Okay, so that's good to have you back. Okay, and today, I mean, it's no simple webinar, right? We're going to discuss some pretty neat feature and advanced feature of the Zenoh protocol.
We have a lot of things to cover.
Good. So what I would say, without waiting further, shall we start?
So do you want an introduction?
Let's do it at the beginning, yes, as opposed to at the end, because that will leave too much suspense, wouldn't it?
So yeah, I'm Olivier Hécart, and I've been working for almost 20 years on distributed systems. I'm now working on Zenoh. I'm the architect of Zenoh, and especially working on the routing, and
which is what we'll cover to some extent, today. Okay, good. So let me share the screen and let's keep going.
So I will present you some protocol improvements that we introduced in Zenoh those last months. And the first improvement we did is the interest protocol that was introduced in Zenoh version 1.0 and which greatly improves Zenoh scalability. So before getting into the details, let's step back a bit and speak about many-to-many communications in general. So if you want to perform many-to-many communication, a very simple strategy is to broadcast and to apply your data filtering at the reception side. The obvious downside of this strategy is that all the data is flowing everywhere and you are consuming a lot of bandwidth everywhere in your system.
And by the way, although this sounds crazy, this is what most technology do.
Yeah, and in some very specific use cases, it could be the best. But it's very as soon as the system or the networks gets bigger, it's quickly start to be a no-go strategy. So what Zenoh does is to propagate subscriptions in the network, and that's what it did until V1. So that you can apply your data filtering at the sender side. And so you fully optimize your data plane. Data only flows if there are subscribers and on the path from the publisher to the subscriber, the one or the many subscribers that need the data. So that's good for the data plane, but the downside is that you propagate subscriptions everywhere. So the first thing to notice is that obviously Zenoh squashes subscriptions. So if you have in one part of the system 1,000 subscriptions for the same key expression, the rest of the system only sees one. But overall, if in the system you have different subscriptions and different key expressions, all those key expressions are propagated in the system everywhere. And so this is probably, in most cases, better than doing broadcasting, but the downside is that the publisher has a lot of state to maintain because it has to know all the subscriptions of the system.
And again, so that might not be a problem for some publishers, but for some applications, especially on embedded devices, that might be
a small sensor.
Maybe you don't want, right?
Yeah, you don't want a small sensor to know all the subscriptions in the system. And moreover, most of the subscription doesn't concern it at all, probably.
Yeah. And by the way, you say all the subscription, but it's also true that, so as you mentioned, there is squashing and there is a form of generalization, right? So we might provide, I would say, less detailed.
Yes. Still, it's a lot to handle for a microcontroller.
At a very large scale systems.
Yeah. So, from Zenoh version 1, out of the box using the put and get operations, Zenoh only propagates subscriptions to the routers, so to the infrastructure of the Zenoh system. And publishers, peers or clients, whatever, they send all their publication and their queries, by the way, to the nearest router, and the filtering happens in the first router. So this is already a far better compromise, as the subscriptions only flow in the infrastructure and the data path is not fully optimized, but overall better. But the downside, indeed, is that, for example, here, the publisher publishing on W/1, nobody is interested, and the data still flows to the router. And so here is where the interest protocol kicks in. The interest protocol allows some application, typically publishers, to query to the router what are the subscription matching their publication. So using the declare publisher or declare query operations, when calling those operations, an interest message is sent to the nearest router telling, okay, I'm interested into the subscription matching my publication key expression. And the router replies with only the subscription that match this interest. So here we have the best of the two worlds, because now the data plane is fully optimized. Data only flows when there are matching subscribers on the path to the matching subscribers. And the publishers only get the subset of the overall subscription that may match their publications. So yeah, that's how Zenoh now works since V1. Now we can get a little bit into the details. I will not go too much into the details, I hope. But here you can see the interest message. So mainly you can ask for the current subscriptions, queryable, or the future, or both the current and the future ones. And you can ask for key expressions, you can ask for subscribers, you can ask for queryable, and or liveliness tokens,
which we'll cover later on.
Yeah. And this is a quick overview of how this protocol behaves. So the node A here sends an interest for subscribers to node B. Node B sends back all the subscriptions that are currently known matching this interest, and the declare final to tell the node A, okay, now you know everything that you have to know for now. And so node A can start doing writer-side filtering from this declare final, because I have the full view of the current state. And then node B, if future subscription were asked in the interest, continues propagating new matching subscribers or undeclared subscribers if some subscriber disappear of the system, until eventually node A sends an interest final saying, okay, I'm not interested anymore into those subscriptions. So that's it for the interest protocol. Any questions, Angelo?
No, I think that was pretty clear. And
Okay.
So, and I think one of the main reason we put this in place was improve scalability, and by the way, allow full control, especially on the embedded nodes, right?
Yeah.
Because especially for a Zenoh Pico application on a large-scale system, you never know what might hit you, right? And as much as Zenoh discovery information tends to be as compact as possible, still in an open system, you don't know. And I think the big advantage of the intent protocol is that once again allows you to dimension your application and make sure that you can really bound resources even in a completely open system, because you have defined your intent or lack of intent, right? You understand what are the consequences, and I think that's quite important.
That basically turns the declaration protocol from a push protocol to a pull, where you have far more control on what you pull.
Yeah, and we push up to when it makes sense, and then where we need to be a little bit more gentle, right? We allow the choice of exactly.
Okay, so then from V1, we started putting most of our effort into reducing Zenoh resource consumption in terms of CPU, memory, and especially during the initialization phase of Zenoh. So we did this in multiple steps, and we are still working on that. But in Zenoh version 1.1.1, we changed the way we scan network interfaces to scan them far less often, as this is a very costly operation.
Surprisingly
Yeah,
costly
yeah,
operation.
very costly. We introduced some new option to the gossip protocol that we will cover later, that minimize traffic and message treatment. We also pre-computed less routes compared to before. And then in Zenoh version 1.2.1, we completely removed any route pre-computation and moved to route lazy computation, only computing routes on demand.
And here you're referring to routing routes. So on the
Yeah.
routing subsystem of Zenoh, right? Which isn't necessarily on a router, but it's in
Well,
fact,
it's necessary to have the data plane and the critical path not too slow to
Yeah.
pre-compute those. But here we only compute routes we know will be used, because by pre-computing routes we have to guess somehow what routes will be needed or not. And even if the guess was improved in V1, it's still better to only compute what you need.
you are
for
sure that you need, yes.
And now we introduce in main, that will be released in the next Zenoh release, some strategy to limit the number of TCP connection or transport connection in general that occurs between the different peers of the subsystem.
And that has also good impact in reducing memory utilization
Yeah.
because of buffer allocation and so on and so forth. Yeah.
So we already had a lot of improvement in V1, but in the next slide I will show you the benefits we gain between V1 and V2 with the lazy routes computation. So those are the results of a test we do with ROS2. So we start 100 ROS2 nodes in a single host, but using the transport, right? So 100 ROS2 process, ROS2 nodes. And then we see how much time on CPU consumption it takes to set up the system, right? And you see in V1, it was using 100% CPU for 17, 18 seconds, and the system started to be functional after 17, 18 seconds. Now it only takes 7, 8 seconds for the system to be fully functional.
Yeah. And again, I think for those that are not familiar with ROS, and especially how the RMW maps to Zenoh, it's worth knowing that it's pretty articulated mapping. There are various different publisher subscribers, liveness token, right? If there are parameters, and there are parameters by default, each of those entails, once again, queryable. If there are services, again, those are queryable. With action, it's queryable, and a bunch of publishers. So a node entails quite a bit of Zenoh stuff in that respect. And so 100 times that, it's quite a bit of matters.
Yeah, a ROS2 node in Zenoh term is quite of a heavy node. It has a lot of Zenoh entities.
Exactly.
So it's a good test. That's it for the cold start, and let's move to gossip scouting. So before speaking about the new target option we introduced in the latest release, let's have a step back and maybe try to explain gossip scouting in general. So a gossip protocol, also sometimes called epidemic protocol, is a way to propagate data in a peer-to-peer system where things spread like an epidemic, right? So nodes propagate information on behalf of the other nodes, and from neighbor to neighbor, things propagate like this. So in our case, we don't use that. We use it to propagate information on the node that exists on how to connect to them. So we use a gossip protocol to propagate what we call hello messages on locators of nodes in the system. So typically, if you have a system running and you want to use one node as a rendezvous point, could be a peer or a router, that's why it's drawn like this, you can configure a new peer with the locator of this rendezvous point. Note that you can use multiple nodes as rendezvous point for fault tolerance, because we don't want this rendezvous point to be a single point of failure.
Absolutely.
And so we can use multiple nodes as rendezvous points. But now we start this peer with locator of this rendezvous point, it connects to it. This rendezvous point says, okay, hello, I know those two other guys, and here are the locators. And so now that this new peer can connect to all those new nodes.
And again, this is so. Some people cannot use multicast, right? In other environment, multicast is forbidden. So it's not that they can't just stay. It's forbidden by the sysadmin. And in other environment, it's just not available. And for many technologies or many other technology, when multicast is not available, then configuring and having incrementally adding nodes to your system becomes very complicated, right?
Yes.
Because all of a sudden, it's about providing the list of whoever else is in the system. And the gossip, it's in that respect very powerful because it doesn't require any UDP multicast, right?
No.
As you just explained, you have one or multiple rendezvous point, which potentially I could even discover by DNS, right? Could be a DNS name, potentially, with DNS load balancing behind, potentially even, right? And then it's that anchor point that allows me to do the closure of the rest of the system, which is quite powerful. And so if you're in a data center or in any system across the wireless network, where multicast also is very, very complicated, right? This works incredibly. It's an essential add-on, and this is the reason why we had this kind of discovery since the very early days in Zenoh.
Indeed. Yeah. So what you should note here is that once this peer is connected to the other ones, those other peer will also send them the locators of everybody they know. So everybody will send to everybody what they know about the system. And if you are purely peer-to-peer, this is usually what you want, because there is no main node, and so this is fine. But
and it's self-healing too, right? That's the other advantage.
But if you are using some nodes as rendezvous points, some special nodes, could be a router typically, then all the traffic going between the peers, once they connected, is extra, is useless. You don't need it. And it's quite some traffic and treatment that you may want to avoid. So that's why we introduced the new target option that allows to tell, okay, so in this case, for example, the router should send gossip message to everybody, but the peer should only send gossip message to routers. And so if you look on the right, the gossip protocol will happen on the blue links, but no gossip protocol will occur on the white links, as the peers are not supposed to send any gossip message to other peers. And when the number of peers increase, you are saving a lot of traffic on treatment.
Yeah. And there is more on this, right? Because the target option can also be. Are you going to cover the ID story?
No, not here, but we can speak about it. So the last point there was in the list, and maybe I can go back to this list. Yeah, the autoconnect strategy option. So when two nodes discover each other one way or another, they both try to connect to each other. And if this happens exactly at the same time, they might end up being both connected. Having established two connections in the two directions. If obviously the first connection happens before, and then the second one will not try because I'm already connected to this other peer. But if it happens really at the same time,
there is sufficient concurrency, right?
Yeah,
that's concurrency in
so
action.
And you end up with more TCP connections that you need. And so, we added an option to have some strategies, and we for now implemented one strategy to say, okay, let's only connect to the remote peer if it has a higher Zenoh ID than myself, or the way around.
So we break the ties, we make a total order. Yeah.
So in a LAN, this works perfectly because everybody has a public address, anybody can connect to the other one, and so you're sure there is only one way of connection, and
you save resources. Yeah.
If your peers are across NAT, then you should go back to the
maybe. I mean, I think it really depends on the deployment. So it's good to understand what you can control, right? And I think that the Zenoh principle is always to make sure that you can use the least number of resources, right? And then give you more flexibility when you need it. Because even with nuts, if we are both behind the nuts, right?
Anyway, we need to go through the router.
Exactly. Or we would have to do some hole punching, right? So I think it depends, but it's good to
Well, the classic strategy gives you more functional strength. You're pretty sure things will connect if they can.
Correct.
The second option,
you have an assumption of symmetry.
Yeah,
indeed.
Okay, and last part of this presentation is about connectivity monitoring. So this is something that exists in Zenoh for quite some time now, but
not very well known. Still quite asked, right? Because I think we get questions.
It's a good opportunity to cover those. So Zenoh offers three main ways to monitor the connectivity of your application with the rest of the system. From a lower granularity functionality, but less expensive, to a most granular liveness tokens option, but with a slightly higher cost. So connectivity status and events. By simply issuing a query on this key expression add/star/session/star, or subscribing to this expression, you will get samples with a key like this, where you can see your local ZID, you know it, but you also see the remote ZID.
Yeah.
You can put when it's a new transport and a delete when it's a closing transport, and a value which will contain some more information about this transport in a JSON format. So maybe we can just demonstrate this very quickly.
The best way, yeah.
So I will just use the sub example.
Okay, you might want, if you can, to increase just a little bit the size, just for the benefit of people that don't have a big screen on big screens online. I think that should be good. I think should be pretty good. Yeah.
Okay. So it's subscribing, nothing happens. Maybe I can start a router, and now you see, okay, my subscriber received the put and say, okay, there is a new node with this ZID, which is a router that just connected to me. So here you only see what's connected directly to you. And you have more information about the links, because one transport between two nodes can be composed of multiple links. In this case, is one link, one transport, but you get the detail. But if you are only interested into transport, you only link into those keys. And then, for example, I start another node, and immediately I receive, again, a notification there is a new transport opened with me. But this time, it's a peer. And now, if I close this one, I receive some delete. And if I close the router, I receive some delete again. So I can tell what I'm connected to right now. Am I connected to a router? Yes or no? As a client, for example. As a peer also, am I connected to a router? How many other peers am I connected to? Who are those peers?
So concrete example, right? I'm using Zenoh Kotlin API for making a mobile application.
Mm-hmm.
Usually I need to know if I'm connected to a Zenoh infrastructure node, right? How do I know that? the best way is potentially to use this kind of notifications, right?
Yeah.
And this is also something else that sometimes, well, let's say if I'm a client, then I wouldn't be able to open a session unless I find a router. But if I'm running as a peer, this is something that sometimes people, I think, have a hard time understanding. A peer doesn't need anything, right? He's happy even alone.
Yeah.
Right.
He's
So
happy being connected to nobody.
Exactly. It's perfect. It's then, right? So when you open a session on a peer, you're not expecting necessarily to discovering anything. And then if I need to know if I found a router or anything else, and I need to display it, for instance, in my application, how can I do that? Well, that's one potential use of the connectivity status, right?
Yeah. Indeed.
Yeah.
And so
any other idea for the users?
Well, I think those ideas are good, and you can start maybe if you have heavy treatments, maybe you can only start them when you're connected,
for instance,
and stop them when you're disconnected or something like this. And this is purely local, right? This is information Zenoh already got. Am I connected to something or not?
Exactly.
And just so it's very cheap in terms of resource.
Yeah.
But it only gives you local information what my process is connected to, and it's only black or white. Am I connected or not? Right. So the next functionality is matching status that you can get when declaring a publisher. Okay. So once you've declared a publisher on a given key expression, you can ask for its matching status. I should not click. You should ask for its matching status and ask for its matching subscribers, and this will return you a boolean. Are there matching subscribers, yes or no, for this publisher? So already it's a bit more fine-grained because you know for this key expression if there are matching subscribers. And again, this could allow you to start or stop the heavy treatment that is needed to publish the data. For example, if you are publishing video frames, do you need to encode them or not?
Or if you are if you are capturing images and then doing feature extraction, whatever, are you going to do through all that work? Because in any case, it's CPU time. It's going to be network, so it's going to drive down potential power if you are battery powered.
So you can simply get this status, or you can listen to it by declaring on your publisher a matching listener. Then that can then behave like a subscriber. You can provide a callback or use the stream API like in this example, and you will receive updates, and each time matching subscriber is turned to true or false.
So Olivier, I tell all the time that publishers don't exist in Zenoh, but then we always have those in the API. So do they exist or don't they exist? What's the reality?
So they exist locally, and it's the first hop. So because how does this work?
So I think it's good always to explain, right? Because I always mention that you don't need actually a publisher to do a publication, and the publisher is just an optimization. So it's always good to explain what are those optimizations.
So as we have seen in the first part of the presentation, when you declare a publisher, Zenoh sends an interest to the router, saying, I will publish this. So now I can do writer-side filtering, because before I couldn't. I had to send everything to the router. And also I know my matching status suddenly, because now I know there are subscribers matching my publisher or not. So, but then the big thing is that publishers may go to the next router, but no further. It's not propagated in the system, while subscribers are propagated in the infrastructure.
Subscriber and queryable, in fact.
So matching status. So the limitation obviously is that it's a true or false thing again. So it's per key expression, but it's still a true or false thing. Do I have matching subscribers? Yes, but how many? I don't know.
But again,
which ones? I don't know.
Which is good, right? Because as we know from previous life, when you try to get the details, it
Yeah,
doesn't
but
scale.
sometimes, yeah, you need to do a choice. Sometimes you need them, but you have less
I agree.
scalability.
But the point is,
It's a good point to
you
choose.
pay if
Yeah,
you need for
yeah,
it, right? You shouldn't pay
exactly.
all the time. That's the key principle.
So if you want more granular information, like I really want to know how many subscribers are there, which ones are there, and so on, you should use liveliness tokens. Uh, so as you see in the first line of code, every application can declare some liveliness tokens that they can identify with a key expression.
Yeah.
And the lifetime of this token will be tied to the lifetime of the session and so the process that is declaring it. So you can undeclare them explicitly, but if you die or crash or whatever, the lifetime of this token is linked to you. Also, if you crash, the token dies as well. And again, you can get the tokens, which work like a classic get, and that you can use with a callback or a stream API again, and you can subscribe to those tokens, which also works like a classic subscriber. And so this allows to tell you what are the tokens around that are currently alive that match this expression. You know if you can know when they die or when you lose connectivity to them, and I will show that
Yeah.
right
And
now.
again, this is super powerful, right? Because essentially what we provide as part of Zenoh, I mean, the way in which I like to look at liveness token is like group management, because in reality, we are able to define a group and do group membership, right? So we can detect who is joining, so who is declaring a liveness token, who is leaving, because either they've dropped the liveness token or because they've crashed. And we can do that with subscribers, as you showed in the API, or at any point in time, I can query the liveness token and have a view of the group, which is very powerful, right? Yeah, anyway.
So here I start a Zenoh router, and I will use client mode for this example to more easily break the connectivity between my applications. But here I start the sub-liveness example connected to this router. And so it's subscribing to all tokens matching this expression. For now they are known. But if I start another application that declares a token matching the subscription, okay, I see there is a new live token with this ID. And now if this application crash or stops or is killed by the user in this case, then you
Gone.
see token is gone. Another example is that I restart the application, the token is back alive, but I kill the router. So this client lose connectivity with this other application, with this token, cannot know if it's still alive or not. So considered dead.
But that's a problem of distributed system, right? We know connectivity is
Yeah,
gone.
but the
Then
good thing is that even if it exists, I cannot communicate with it anyway. So
literally there is a network partition right
yeah,
now.
yeah,
So for what we can tell, it's gone.
exactly. Okay, so that's it for the protocol updates.
Come on. I think you're going to make a cool demo.
And yeah, so the
I thought you wanted to stop here. Okay.
Well,
I almost had a heart attack, Olivier. That's the coolest part still to come.
so it's
right?
a demo we have been doing for quite a long time,
But not so many time to the general public. In fact, I think we never did on a webinar, and it's super cool because it shows the real power of Zenoh routing.
Yeah, so the goal of the demo is to show the dynamicity of the Zenoh routing, dynamicity that allows to optimize things when applications are moving around like robots, cars, vehicles, and also grant us some fault tolerance, because when things are dynamic, they adapt to change and to failures.
So self-healing of the
And another point of this demo is to show the tooling.
Yeah, absolutely.
So let's start because the time is running. So
don't feel rushed. I mean, take your time.
I just started 14 Zenoh routers on my laptop that are interconnected a given way. And to visualize this, I will start the Zeta tool. So I'm monitoring some Zenoh applications here. Let's connect. So and use a network map. Okay. So I need to untangle this just a bit. Okay. So
good.
those are the routers I am running and the way they are interconnected. And here we can see the tool is connected to one of those routers. And you see that there is currently no user traffic going on in this network.
Can you zoom in just a tiny bit?
I will try, but it's sensible.
Yeah.
Because
So that's good.
okay,
I think that's pretty good. Yes.
Okay. So now I'll start a Zenoh application that is capturing the
webcam,
camera as a webcam and connected as a client to one of those routers. So here it is. It's publishing some video frames, but as there are no subscribers in the system, nothing flows. But I am now starting a second application that will subscribe to connected to another node and will subscribe to those video frames and display them. So hello again. This is what is received by the second application. And I will let that in the background, but we can still see a bit of it. And here is this second application. I will just move it a bit so that we can see better. And we see that data is flowing along this path in the system.
Yeah.
Okay. So now let's assume those two applications maybe are robots running in the factory, driving in the factory, or vehicles
driving
moving
along,
around in
the highway or whatever. Yeah.
In a city. And there are multiple ways to detect that those things move on if they are using a routers closer to their new geographical location. But for this demo, I will just instruct this application to move and to connect to a new router.
And again, which is also a valid use case, because I might want things like car or robots to automatically switch to the closest infrastructure element, or I might have something that optimizes on top, coordinating that, right? And with them, you can actually do both.
Yeah.
Right? So here we are showing what a control plane, an intelligent control plane would do potentially to rewire connectivity as things move around.
So here I will tell the capture application to connect to another Zenoh router. And so basically, by the way, I'm using the REST APIs using curl to send HTTP requests.
Yeah.
And you see that it connected to a new router, and the new route has immediately been established, and the data is still flowing. So maybe I can do this.
You should do it while waving the hand, because otherwise, yes. I mean, so you see that there is no effect.
Here the latency is very good as I'm localhost,
unperceivable,
but
yes.
The
principle,
middleware itself, if the latency is good enough, can do the rerouting very efficiently. I can also move the display application. Okay.
And again, you should do it while moving.
Yeah.
Otherwise,
Indian nodding.
Okay.
Let's maybe move back like this, so that okay. So and you see that. So maybe.
Oh no! I know what you're going to do. You're going to kill some routers.
Yeah. No. Don't do first,
that.
I will move them back. Maybe.
Okay.
Like this. So one good point is that we keep functionally working right while moving, but also the closer we are, the best latency we have, because the most optimal path we get between the two applications. Okay, so let's move them back apart so that. Okay, and now let's see what happens if I kill one of the routers. So this one. So if I kill the router again, the automatic rerouting occurs and new routes are selected. If I kill yet another one, rerouting occurs and data is still flowing. And if I restart them, let's restart the middle one. Okay, so rerouting occurs. So in this case,
well, in this
didn't
case,
need
it
to,
doesn't, because you,
didn't
you
need to
don't
use,
gain,
yeah.
you don't gain anything in
The new
terms
path
of
was not
path,
better
yeah.
than the old one, but sometimes,
If you start yet another one,
yeah,
now you have a
a
better
new
path.
route is
So yeah,
selected, and yeah.
yeah,
So yeah, so you can, so yeah, here you can see how dynamic the Zenoh routing is, and you have a quick over tease, let's say, of the Zenoh tools.
yeah, absolutely. And so dynamic, how dynamic it is, and the support for migration, right?
Yeah.
Which is, yeah. Okay, cool. I guess it's up to me now to do some presenting. Is it?
Yeah,
Okay,
please.
So thank you again, Olivier.
You're welcome.
And let's quickly switch to my part. Up. Okay, let me pull up the slides. Here they are, ready to go. And my screen should be visible in just a moment. Okay, so a few more things that we had listed on our webinar. First was share memory and zero copy. So, I mean, this is still somewhat surprising for me, because we have had share memory and zero copy since version 0.5. I don't know if you recall that.
I don't know the exact version.
Okay, I'm that maniac. Okay, and so it's something that we have had for a very long time. I think that we don't talk a lot about it, but obviously there was some major improvement that was done in 1.0 to better support automotive and robotics market. And so I want to cover once again, what Zenoh can do today in terms of share memory and the API. I also saw a couple of weeks ago some questions on Discord, and I'll address those, at least one of those, in this section too. Okay, so first point, we have had share memory and zero copies since version 0.5 of Zenoh. And the other important thing is that since the very beginning, we had a pretty Zenoh-like take on share memory, which is different from anything else that was there before. Why? Because instead of doing what everyone else used to do, which is have a single share memory segment that everyone taps into, Zenoh started it since the very beginning with share nothing, meaning everyone has its own share memory segment. And the idea is that I loan you buffer out of my share memory. There are a series of advantages of that, but one is dimensioning, okay? Because it's much easier to build systems that are incremental, because everyone brings its own segment in a way, and you don't have a single segment to dimension, which you never know how big should be, okay? But there are some other advantages. Now, in the 0.5 version of up to, I would say, pre 1.0, there was an assumption that we had in our share memory implementation, was that in order to be able to properly manage and safely manage the share memory buffer, share memory could be used by peers or routers, but let's say it's an application that were running over a click. Okay, so everyone directly connected to everyone else. Okay, why? Because that was the way in which we could easily trace use of our buffer and eventually reclaim them. That didn't allow us to support this kind of architecture that are very important for zonal architecture in automotive. And as version 1.0, we extended our share memory to be zonal architecture friendly and make it possible to do share memory within a share memory region. Okay, so that the simple version of that would be within a host. Okay, but life is more complicated than that. Even when having routers. Okay, and so since version 1.0, you have no topological constraint. We still maintain a distributed memory management. We have now safe mutability. Okay, so we are able to detect if a shared memory buffer is still in use, and if it isn't, you can safely mutate, get a mutable reference of that buffer. That's very useful when you want to do software pipelines. We introduced the concept of shared memory provider, as we will see. So pre 1.0, we only supported POSIX shared memory. But again, sometimes you need to tap into specific hardware share memory, GPU share memory, gods know what kind of share memory. And so we needed a way to allow our user to provide interfaces to those source of share memory so that we can manage it, okay? And that's done. Custom layout. So in some application, for safety reason, you need canaries or safety zones to be able to detect overflow or underflows. That's also supported. And again, we wanted to make sure that all of this could be done by having minimal CPU and network overhead. Um, Now, in terms of architecture, there is now a concept of a shared memory backend, and the only shared memory backend that is available in the open source version of Zenoh is a traditional POSIX shared memory backend, and then shared memory provider that go and tap into the shared memory provided by backend and manage it essentially. Okay, so here you see an example of the API, and in this example, which you will find also in the distribution, we are creating a POSIX shared memory provider backend, okay, that then is used to create a shared memory builder with a protocol ID. This protocol ID are used to make sure that we can always tag buffers with the kind of shared memory out of which they were coming. Because one shared memory buffer coming out of POSIX backend or GPU or Qualcomm specific hardware, we need to be able to actually distinguish between those, and that's the role of the protocol IDs. Okay, and actually once you have a provider, at that point you can just allocate memory very simply using the alloc operation. And there was a question, I think, I think it was 1 week ago, perhaps. Someone was confused by, why do I need to use a layout? I'll cover that in the next slide. But in fact, you don't. You don't even need to know what is a layout or why you would want to control a specific layout of your buffer if you don't have that requirement, or whether you want to control the alignment if you don't have that requirement. But you can allocate just by using the alloc operation on the provider, and that just works, okay? That's the simplest way. So what you see here, provider.alloc wait unwrap, that gets you a shared memory buffer that you can fill in with whatever you want, and then use in a to reply a query to do a put operation. In fact, wherever Zenoh would take a buffer, you can pass a shared memory buffer. Zenoh will do the magic, where the magic means that any receiver that is in the same shared memory domain will just receive some meta information on how to access that shared memory buffer, and everyone else will actually be sent serialized data over the network. Okay. So you can specify layout if required. That's not mandatory. So in this case, for instance, I'm defining a requirement for alignment, but as part of the layout, I could also define canaries. There are multiple ways of defining the layout. And once I've defined a layout, that you have to think as a blueprint for what I want to allocate, right? I don't want to specify the layout or the canary size every time. So I specify a layout, which is a blueprint of how I need to allocate my buffer. And then boom, I just do alloc on it and I'm done, okay? And garbage collection and defragmentation are under your control. Okay, so what we do in Zenoh, we keep track of references, okay, and we do that actively. What we don't do actively is to clean up memory or defragment. Why? Because we don't want to add any, especially for embedded system, any CPU related activity, right? Under which that is not under your control. So the principle of our shared memory hasn't changed, was always the same. You have the hand on when you might try to garbage collect and when or if you try to defragment. Once again, garbage collect, why? Because we know exactly what is in use and what isn't. But unless we make a scan, right, of the shared memory provider, we don't know what we can move to the free list. Okay, and so the garbage collection is literally a scan. So it's rather fast, but it's still something that we think should be under the control of your application, and that you can decide to run periodically if that's what makes sense for you, but it's under your control. You can decide to run it as a consequence of an allocation. I try to allocate. I don't have anything more on my free list. Then, as you see here, I could use with policy, block on, let's ignore for a moment the fragment. Suppose I only garbage collect, then this would try to do a garbage collection. So as a result, all the free buffer would be put on the free list. And if there is a buffer now in the free list that accommodate my allocation request, then this would succeed. And if that buffer doesn't exist, this will fail. Okay. But that doesn't necessarily mean that I don't have enough memory. It might mean that buffer, there might be adjacent buffer that if merged back, right, they would have exactly the appropriate size. And this is where the fragmentation come into play. So you can also decide that when you can't allocate, you might want to garbage collect and defragment in that order, right? Which means we would do a scan of your share memory, regenerate the free list, and as we do that, coalesce all the buffers that are contiguous so that you end up with as big as possible buffers in your free list. And then we will reapply our allocation strategy to get your buffer. Okay. Again, this is under your control, and you can decide whether you want to run the fragmentation garbage collection as a consequence of a lack of memory when trying to allocate, or periodically. Any other remarks on this, Olivier?
Well, one little thing we can add maybe is that one challenge with most system share memory providers like POSIX1 typically is that when the application crashes, it doesn't freeze share memory, and you have the share memory segment just remains there. You have no way to control that. It's very painful, and so we put quite a big effort and have a quite interesting functionality that when an application crashes, and even if it is connected to a router in a complex topology, other nodes in the system can detect that this node crashed and free the share memory segment, and and free the buffers they were reading eventually, things like this, right? So we have a quite interesting watchdog mechanism. That allows this.
Good point, because that was quite a bit of work, and we know how painful that is
to manage yourself. Yeah,
correct. Yeah. Okay, thank you for the remark, Olivier. Okay, so the other things that it's worth understanding is that the limit to how you use this shared memory is your creativity. Okay, so I'll give you an example. Sometimes back there was someone that wanted to do polling with Zenoh on shared memory. He said, "Oh, you can't do it with Zenoh." I said, "That's false." That's always my answer by default, because I always I take it as a challenge. No, but it's true. So you want to do polling with Zenoh, it's actually pretty straightforward. The way in which I would do it is that I would expose a queryable. So suppose I want to have polling channel with Olivier. Olivier would query me. Okay, I would return him a shared memory buffer, and I would have him poll the shared memory buffer for data, for instance. Okay, I mean, you can use shared memory buffers as a way also of creating additional communication mechanism, and of which polling over shared memory is one of those. Okay, so that's pretty straightforward to do. It's sometimes that I want to write an example that shows how to do that. I haven't had the time. I think I probably will the next winter break. I will try at least. Anything else, Olivier?
No.
Okay, so interceptors. How are we doing with time?
We are 6 minutes.
I see. So we are doing not too bad. Okay, so in Zen we introduce an interceptor framework, and this interceptor framework essentially allows you to intercept and operate on protocol messages, either on ingress or egress. Okay, So this is true for any Zenoh runtime. Okay. Recall, in general, in Zenoh we have a graph, right? I might receive data and still forward, right? Because of how Zenoh works. And the other nice things is that, as you know, Zenoh supports multiple kind of links, and in general, and as a consequence, potentially we are brought to communicate through different kind of interfaces, virtual or physical, and you can have interceptors that apply to specific, I would say, interfaces. Okay, either on egress or ingress or egress. Now, we have, as of today, well, other important point, at the current stage, interceptor are defined at compile time, right? So there is no pluggable, runtime pluggable interceptors. Maybe we'll support those one day, but at the present stage, it's an open framework. Interface is actually very straightforward. There are two methods to implement by memory, right?
Where there is a factory
Yeah, and
trait
then
to
the
implement,
and then the
ingress
interceptor,
and,
the interceptor
intercept.
trait, which is pretty straightforward. Yeah,
But it's not a public API
yeah.
per se.
And we have two intercept implementation, one for downsampling, okay, and this allows essentially to do flow control on an interface basis, again, ingress or egress. And here you have an example, which we will see in action, which perhaps I want to downsample video going out over Wi-Fi. Okay, could make sense. Imagine that I'm a robot, I'm doing, or a car, or whatever, and I have a local area network, and I'm doing some computer vision within the local area network. I need high resolution, high frequency video. But then for teleoperation, some of this is also required remotely across the internet or across a wireless network. I don't need the video at the same frequency. I could
Or cannot afford.
Or cannot afford, indeed. And most of the time is that you can't afford, right? Good point.
Otherwise, you don't care.
Otherwise, you wouldn't care. Absolutely brilliant remark. Yeah. And so in that case, I don't need to bother as an application developer, right? At deployment time, I just configure the right interceptor. We also have access control. Actually, that is the slide I want to show. Access control interceptors. That's just another kind of interceptor. And they operate, in fact, or give you a way of operating on any Zenoh message and deciding whether they're allowed or denied. So in this very simple example, you see the rules that are used to essentially deny a put. So that's the name of the rule. So see, permission is deny, the message is put. This applies both on input and output. Okay, and this would be for this interface here. Okay, and for the sensor /*, the subject would be the interface would be EN0. On my Mac is actually wireless network, and then the policy would be deny put on interface. So you apply this rule on the subject, and the result is that in fact there is nothing that is flowing across these two subsystems, if that is what you wanted. Okay, that's just another example of interceptor, and that's how you can configure those. But let's see this quickly in action. So Olivier was showing a video application. So what we're going to do, I'm going to start the video capture on my laptop, a video display on my laptop. Olivier is going to start a router on his machine, and then I'll start a client on my machine that subscribes to the same video flow from the router. That said, the video capture is configured to downsample everything that goes over the wireless interface, which is EN0 on my Mac, to 1 frame per second, okay, which is what you see here. So if we do that, okay, so if we move here, okay, I'm going to show real quick. So this is the configuration, okay, as we saw on the slide, there is nothing different. So I'm going to start here the screen capture by providing the configuration file. I'm going to start here the display application. So you see here there is no frequency reduction, okay. And what I'm going to do now, so you still have the same API, right?
I
think,
so,
yeah, I don't think it would have
no
changed.
reason
There is no good reason, yeah. And here I'm going to start now again a Z-display application as a client of Olivier router, right? Which is, by the way, yeah, so I'm going to start this. And what we will see is the difference, right? Because you see on one side, everything moves smoothly. On the other side, you have 1 frame per second. Okay, it's like a, if I do that, like a watch, like the seconds of, yeah. So that's just a simple example, but just to show that works. And how simple it is to get it configured. So going back to our slides and starting to wrap up real quickly, serialization framework. So first of all, why do we have a serialization framework in Zenoh? That's always a good question. Well, there is no lack of serialization framework, right? And everyone has its own favorite, whether it's Protobuf, Avro, whatever, you name it. And again, in Zenoh, we are not just trying to replace your favorite general purpose serialization framework. The main reason why we wanted to have at least some basic support for serialization were 3. Okay. We didn't want to add or to force a Zenoh user to add yet another dependency on deeply embedded frameworks, because most of your favorite serializer are usually not available on some of the embedded platforms that we run. Okay. And if they're available, there is another problem. They are not certified. Okay. And so we are kind of stuck, and our users are stuck. And so we wanted to reduce one dependency for deeply embedded platform. We wanted to provide a serialization framework that is certified. Okay, it can be certified, and for everyone else, right? We wanted Zenoh to just be Butter included. Okay, because for 80% of the application you do when you get started, the Zenoh serialization framework actually works pretty well. And then you could use it as building block to serialize arbitrary complex types. So what does it support? So we focused on very efficiently supporting primitive types. So integer, floating point, integer in the case of Rust, that's from U or I8 to U and I 128, and F32, F64, okay? So integer, floating point, Boolean, and strings. And then container types. So you can do tuples, arrays, vectors, and map KV for any K and any V for which serialization is supported. Okay? And you can compose all of this as far as anything that you put into something that is serializable is serializable. The result will be serializable, which is a nice property. How hard is the API? It's extremely hard. In fact, there are just two functions, Z-serialize, Z-deserialize. The implementation is actually pretty neat because, when I looked first at what the guys did, and I was expecting a macro, okay, on the outside. But in fact, the macro is on the inside. It's pretty neat. I don't know if you've looked at the implementation.
Not in details.
It's pretty neat, okay? Because it looks like, if you look at the API, it looks and feels, and if you look at the signature, as if you are having type overloading, which Rust doesn't support, right? But then uses macros internally to play some tricks. So pretty slick. And again, you have an integer, okay? Serializing just takes a Z serialize, and deserializing is just the Z deserialize. Likewise for a vector, an hash map, a tuple, an array, and so on and so forth. Okay, so that was my last slide. So in conclusion, Olivier. So we keep adding lots of features. I think there are still a few interesting that we plan, but short term, as you mentioned, big focus has been and will be, I think, until probably April, resource consumption, right?
Yeah, scalability, resource
consumption, and especially
memory consumption. So we didn't cover that, but we are
and that's especially on the Rust portion, right?
Yeah.
Because
but that impacts the C and Python bindings.
Of course. But what I meant is that, I mean, Zenoh Pico, in terms of memory utilization, as of today, that's quite fine. And it's sometimes it's challenging, right? Because we have scenario in which you might have a router that is just one router on a high-end machine serving lots of clients, right? Where resources is not. Yeah, but we have other scenario, like the ROS case, in which we have a zillion of processes on the same host. And this is the use case that we are also optimizing, and I think will further extend the applicability of Zenoh beyond of where we've been so far. Any final remark, Olivier?
No.
Look, it was great having you here, as always.
It was a pleasure.
My pleasure.
And thank you, everyone, for watching.
Yeah, absolutely. And but we are not done, okay? No. Because maybe they have some questions. So let's check if there are any questions. So let me go. Let me stop sharing my screen. And let me see. Okay. Okay, so I don't see any questions yet. It's always like that. I mean, there are never questions, and then once answer a question, ask a question, then it's an avalanche. So we need someone that is not timid to ask the first question. Otherwise, I'll ask you, Olivier, some questions. And let me check if we see. Oh, let me ask you, what is your favorite Zenoh feature?
Oh, good question. My favorite, excellent question. I don't know, but maybe. Well, I don't know if it's a feature, but it's the ability to run multiple transports, multiple topologies. It's adaptability. Right, you can have peer-to-peer local network on the router. Maybe they're using UDP locally or quick, and then TCP connection, and maybe some serial on the other side because there is in a robot some microcontroller connected through USB serial to and Zenoh from end to end with different topologies and
routing data across all those.
Yeah.
And this is still surprising to many people.
And just the PubSub, just a bit. So, and there is co-reply, and there is liveliness, and there is all of them. But even doing PubSub like this is already a relief for a lot of users.
Yeah, for me, it's the combination of the power and at the same time the simplicity, because the API remains pretty straightforward, right? That's the beauty of it. Today they don't want to ask question. Then, I mean, what can we do?
We are very clear.
You want to ask me a question? Okay, we have to censor the transmission. I should have never said that. Okay, but you are the guest.
No, your presentation was also very clear.
Okay, so. Then I guess we are done. Then we suppose, and we are 10 minutes over the time.
We can always answer the questions on Discord.
On Discord, of course. Yeah. Okay, then thank you, everyone.
Thank you.
And thank you again, Olivier.
Yeah.
Ciao.
Bye-bye.
Bye. Bye-bye.